Hello, my name is Andres Nam, and I'll try to explain to you how the Floyd-Warshall algorithm works. The Floyd-Warshall algorithm is an algorithm to find the shortest paths between all nodes in the graph, in a weighted graph. It's a relatively slow algorithm. Its runtime complexity is v on the power of 3, where v stands for the number of nodes. So first, I would like to explain to you what the input for the Floyd-Warshall algorithm is. It is a matrix which is in the size of n times n, where n stands for the number of nodes. And each cell in this matrix represents an weight of the edge between certain nodes. How this matrix is built and how it represents a graph is like the usual case on how matrices represent graphs. We have rows as the source nodes, and now columns represent the destination nodes, and the value on the cell then represents what's the weight of the edge between those two nodes. So for example, here we have this cell here. This means that we go from nodes which labeled 3 to node labeled 1. So I would right now like to explain to you what the implementation of Floyd-Warshall algorithm is. So first of all, as you can see, and as I explained on the last slide, we take as an input a matrix which represents a graph and its edges. We first take the length of this matrix, then we make a clone of this matrix and assign it to this variable called dist. And then we, I'll start with actually these two steps here. So in these two steps, we go actually through each node pair. So I here represents as the source node, and J represents then the destination node. And we do this going through all the node pairs procedure exactly k times. And when we start, we firstly pick k to be the 0th node, and then for each node pair, we now assign to this matrix a distance which is the minimum of what the direct distance from I to j is, or if it's smaller distance, then we assign as the distance to be I to k to j. So in a weighted matrix or weighted graph, this is a possibility, and this allows us to find the shortest path through each node pair. And I'm going to explain this exactly to you later. So in essence, this algorithm, we check if this going from node I to node j directly in this first loop is a shorter path than if we would go through node k. So just summing up both of those distances and picking the minimum. Then in the second step, or let's say if we're going to now consider K1 as this middleman for every node I and j, then we check again if K1 could be considered as the middleman. But then there are a couple of caveats. We cannot forget, however, that when we actually consider now K1 to be this middleman, in the previous loop we already had considered K0 to be the middleman. So when we actually have in this matrix A, I, j value, and we have already done one loop, this actually I to j, this could be both going through the middleman of K0, or this could be going directly from I to j. So these are actually the same thing here. And there is another thing. So when we speak about going from node I through K1 and to j, then actually this could be all of these here. This means that in the previous round, when we considered K0 to be the middleman, we could have, because we actually went through all the pairs of I and j, we could have actually generated that the shortest path to get from K1 to j is through node K0, or an alternative to get from I to K1 is through node K0. Or we could have also found out that the best way to get from just I to K1 is through this direct path, and also from K1 to j is through this direct path. But this means that whenever we now consider a new K to be as the middleman, we have already considered older Ks to be the middleman between all the potential node pairs of I and. So in essence, we have a comparison where, first of all, we have I to j directly, and this is the minimum of either I to j, or potentially having K0 in between, if it makes the distance somehow shorter. And then we are comparing this with now I. So we are potentially now in this time considering K1 as the middleman. We are comparing this with K1 and I to K1 and K1 to j. But we know that here there is also this possibility that K0 has been used as the middleman, or here K0 has been used as the middleman. Because if we were in the last loop, we knew that there was a choice of I to K1 or I to K01 if I to K01 was somehow shorter. So we know that now if we have to set up this I to K1 to j, this is the shortest way we can set up this path from I to K1 to j, because if we consider that in the potential traversal we only have I, K0, K1 and j as the optional middleman that we could use. So this means that this has to be the most minimum graph that we can go through. And here as well, when we speak about now this part here, here we also know that this has to be the minimum potentially, because we have either the direct path or the K0 path, and without any other members, this can be either the min, and we know this is the min. So now if we choose the minimum from here, we know that this minimum has to be the most minimum path that we can take from I to j when we have the option to pick K0 and K1 as the middleman. So this logic becomes important. So we now know that with this subset of nodes available, we can actually now have the most minimum paths for all the nodes I and j. So when we now go to this, so here I have shown also the solution space that will exist for this this example, that there is either potentially I to j as a potential example, or there is I k0 to j, or there is I to k1 to j, or there is I k0 to k1. And then we have created this situation where, because the I to k1 is short thanks to k0, we can use k1 to go to j. And then there is also this option where in the previous loop we have set this path from k1 to go to j. It's possible through k0, or this is the shortest path, and then because it's the shortest path, we can now use k1 again to go to j. So these are all the solutions that potentially could get up to this matrix. So in essence, we now have a situation when we go to K2, we know that in the distance matrix A, we have for each I or for each I to j, the shortest path with potential middlemans K0 and K1 that I explained on the earlier slide. So when we are now in this part of creating this new comparison of whether we should use just directly I to j, we know that here there is the shortest of very many options that we considered previously. We now can compare this to I to K2 and to j. And we know actually here this is the shortest with nodes K0 and K1, either, potentially. And again, this also is the shortest. So if we have the situation where we have to go to set this potential thing up, we have to go through the shortest to this K2, and we know that the shortest path to K2 is this, and from K2 to the J, the shortest path is this, because we created this on the earlier loop. Then we can say that this also, now when we add K2 here, is the shortest path. And then now we can just in a very relaxed manner compare these two, because we know this also is the shortest path considering K1 and K0. So now we pick the minimum from this, and then we will know now that we have this shortest path from K0, from I to j, with a potential middleman of K0, K1, and K2. So this kind of intuitively shows how this, why this Floyd-Warshall algorithm works. Pretty much. So let's remind us that we could have many ways to get from I to K2 and from K2 to J. So let's first look at this edge that we have, AI and K2, where K2 represents the index of the node that we are currently considering as the potential middleman. So in this case, one option is that in the simplest case, actually the shortest distance is going directly from I to K2. But this would mean that there have had been previous comparisons that also consider all of these options here as well. Maybe because we have had to consider in the first stage K0 as the potential middleman. So this is like the second option that AY to K2 could be. Or this would be the option that in the second loop we saw that maybe going through K1 to K2 is the shortest option. But if we chose that option, this could actually mean that this option is represented either one of those three graphs here. Because let's remember that in the first loop, we might have updated that this path that is from I to K1 is actually this path. This can be both, either of them. And also this path here could be now this path. But the general point is we always have each nodes represented as the best or the shortest nodes ever. Shortest nodes considering all the options of K0, then K1. And then when this list of potential options grows, we always know that right now, when we have this direction from I to, let's say, Kx, that this is the shortest route from I to Kx, considering all the potential routes that we can go through Kx minus 1 or Kx minus 2. And the same goes from when we go from A K2 to J.